This video will present an interface prototype of a web-based decision support tool, which was designed to assess and visualize flood hazard, infrastructure risk, and risk to people across the municipality of Valencia. This platform integrates high-resolution hydraulic data with exposure and vulnerability information that aims to support proactive flood risk management. This application was created for the SOTERIA project, which stands for Solution Testing for Regions Through Insurance for Climate Adaptation, and was funded by the European Union. To be able to access the applications, users need to have an integrated modeling account. By clicking the link in the description of this video, you can arrive to this page, which lets you sign up by adding a username and an email. Then a validation email will be sent to you, and you'll have to activate your profile. Please remember to check your spam folder for that. Then there's only one step left, which is to set a password. And once the password is created, the user is accepted into the integrated modeling community. I already have a user, so I just have to put in, and then once we are in our homepage, integrated modeling, we have to go to the profile and groups to join the SOTERIA group. The application is not public, but just by requesting access and being accepted, one can access it. So, for example, I'm already in the group, but if you were not, you would just go to group request and look for the SOTERIA one, click on it and request. And an email will be sent once you have access to it. Then the next step is to just access the application, which is in the link below in the description of this video as well. This is how the application looks at a first glance. We have on the right a map that is interactive, and on the left we have all the observations that we will be able to run. The first step is to set the context. We can either do it by clicking this button, which selects the greater Valencia area at 100 meters resolution, or we can just navigate through the map into an area that we are interested in and select that area. So, for example, if we stop here, everything that is inside this rectangle that we can see will be our area of interest. We could, if not, draw a context, and then we can select what resolution and what year we want to look into, for example, 2020. So now what we can do is make our observations in this context. The first observation that we will run is the hazard. In this case, it's a raster map that has 1 meter resolution, but since the resolution we set for the context was 5 meters, then the results get aggregated at 5 meter resolution. And this is a raster map that shows the maximum water depth for a 20-year return period event. So we can interact with it and see what is the height of the water, the depth of the water. We can also check what values does it take all around the map. And then we have the streams, which are just the streams that are in that. Each of these layers can be downloaded by itself. Then let's look at other observations that we can make. We have the risk to infrastructures or assets, and then the risk to people. Let's start with the risk to assets. We just click on the button of compute risk, and this will give us some different results. For example, we see how it is running each of the intermediate layers that it will need. And those are the 4 assets that it takes into account. So runoff, basement, inundation, and obstruction. These are the 4 types of risk that we have information for. Each of these layers, of these intermediate layers, is run, and we can look at them individually. The values that they take are the level of risk of that concrete asset. And this is the same, well, it's different for each of the risks that we are studying. And then we have a risk counter that just counts how many of these 4 risks are present in each of the buildings. So the values it takes are from 0, where there's nothing, 1, 2, 3, or 4, when all of the risks are present. We can download this layer or each of the intermediate layers. Then we can look at what measures are applicable in this area. There are 5 measures that could be applicable in this study, and the platform can support decision making by assessing which of these is applicable in each of the buildings. The system will compute the spatial layers and indicate us where each of them may be suitable. So, for example, if we look at detention ponds, all the buildings that are recommended to get this adaptation measure are highlighted in the map. And then, same as before, we have a counter that for all the buildings aggregates how many of the different adaptation measures are applicable. It tells us whether is it there's only 1, or maybe, for example, 4 of the measures are applicable in this building. And now let's continue to the last observation that we can make, which is the risk to people. This one is the risk to people is a module that focuses on the pedestrian safety in public spaces that are flooded. So while it computes, we can. So this risk is evaluated by combining the flood hazard that we saw previously with social vulnerability indicators that are at census tract levels. So the result will aggregate a layer that is at 5-meter resolution with other layers that are at a much coarser resolution. But it will identify those areas where pedestrians may be particularly exposed during the flood events. So some of the layers that we could look into are, for example, the density, the critical age of people. So people that are elderly or children might have more difficulties moving when there's flooding on the street. So we have these levels of vulnerability. Vulnerability level indicator has only high and moderate values in this area, and we can see that it has a very different resolution than the flood hazard does, but the system is able to still put together this information to give us the final risk level to people that we see in this layer. It takes values of moderate, then low in the blue areas, high in the red ones. All of these results get documented in the documentation and data flow tabs that we will look at it now. The documentation and data flow tabs are especially important for ARIS because we're not talking of a static model, but a modular AI assistant modeling platform that is designed to integrate heterogeneous data, dynamically assemble the models, and therefore it wants to support the decision-making across different contexts, scales, and users as best as possible. This is why the FAIR principles, which stand for findable, accessible, interoperable, and reusable, provide a framework that ensures that these datasets and models can be understood and reused and also trusted over time. This is especially important because while the model is written and in the system, if, for example, newer data that is at a higher resolution or that is of a newer year can be added, and the machine reasoning will choose the best datasets and models for each of the contexts that is studied. So if someone were to come into this website in a few years and some new datasets were added into our system, the model would be able to take those instead of what is there. So to ensure that all of the steps that are taken in the modeling are understood, there is always a report that gets put together automatically. Every part of the report has been written by a human, but what the artificial intelligence does is choose the parts of the report that are relevant to the session where it is being run. So, for example, in this case, we get the methods for the hazard because we have clicked on the hazard button. But if we had just looked at some other parts, we would not get all of these in the report. The documentation gets automatically created, but the information that it is using has been written before. And we also have here the figures that were created during this session and the datasets that were used. And finally, we have the data flow tab, which is a schematic manner to see what is going on, let's say, behind the scenes, instead of being written in plain English as the documentation is. This data flow explains what are the steps that are taken to get to the final results. In this case, for example, what resource has been used for the hazard layer and how it is transformed to be used into the system, and then how the risk for people is done. It uses the hazard, but then it also uses the vulnerability, which uses density, critical age, and foreign origin, and models them together to then give us some levels of risk. So this is all for the application. That is all. Thank you for watching, and do not hesitate to contact us for any other inquiries.